Okay, so hello and welcome to my microeconomics lecture series. So what I'm going to do here is I'm going to talk about game theory, and I'm going to start by introducing basic features about a game. I'll talk about solution concepts, and then I'll do some examples of solving some games. So the first thing here, in order to be able to model a scenario with game theory, we need to be able to have players, strategies, and then payoffs. So basically we have to be able to say who's involved, what they're able to do, and then what they're getting as a result of what they've done. We can model game theory, we can model a scenario using simultaneous or sequential timing. If we're using sequential timing, we would use a game tree, as I've got on the right. If we're using simultaneous timing, we do a normal form game, one version of which is a matrix, like we see here on the left. Okay, so here's how to just read a basic game. So I'll start on the left. I'll start with a game that's called simultaneous. And so what I mean by simultaneous is that the players are not able to observe what the rival has done prior to making their own selection. So I've got two players in this game. One player is controlling the rows and choosing from strategies of up and down, and the other player is choosing columns, choosing strategies of left or right. And then as a result of their mutual selection of a particular cell in this matrix, they're going to get payoffs. So for instance, if the row player selects up and the column player selects left, then the row player would receive a payoff of 5 and the column player a payoff of 5 as well. However, if the row player selects up and the column player selects right, then the row player gets 0 and the column player gets 10. And then the other cells are picked out by when the row player selects down and the column player selects left, then row gets 10 and column player gets 0. And if column player selects right while row player selects down, row would get 1 and column would get 1. So hopefully you've noticed the first number in the ordered pair goes to the row player, and the second number in the ordered pair goes to the column player. In the sequential version of the game, I have the row player moving first. And then I've got actually two information sets labeled with columns, these two forks coming off. So row player can choose up or down. If row player chooses down, column knows that row player has chosen down and then makes a selection of left or right. If row player chooses up, column knows that up has been chosen and then makes its own selection of left or right. That's why I've put these primes. I put these little apostrophes after I have L prime and R prime. This is to distinguish between two states of the world, right? So L prime is column player's choice of left after observing row player has chosen down. And regular L without the prime is column player's chosen choice of left after row player has chosen up. And then I've got the payoffs arranged below, and you'll see these payoffs coincide with what was in the matrix. Anyhow, so that would be the sequential version of the game. So once we've spelled out a basic game and we've talked about who the players are, what they can do, and what the payoffs are, and we got to make some prediction about what we think is actually going to happen. And so what this involves is invoking a solution concept. There's a variety of different solution concepts. The one that's most familiar, especially in the introductory level, is the Nash Equilibrium. So I'll talk about the Nash Equilibrium. However, to be able to understand what Nash Equilibrium is, I need another definition. So first I have to define a strategy profile. A strategy profile is a list of strategies, one from each player, that's going to specify the outcome of a game. Right? So a strategy profile is going to be a list of strategies. So in this game I've got one such strategy profile would be up, right. Right? So up, right, it's one strategy from each player, and it's going to specify a particular outcome of the game. In particular, the top left, the top right cell in my matrix, right? So here are my other strategy profiles. Each of these games have number of strategy profiles. In the game on the left, actually, there's just 4 strategy profiles: up left, up right, down left, and down right. On the sequential game, we'd actually have something a little bit more complicated, because we would distinguish between choosing left after having selected down and choosing right after selecting down, from the situation where the player would choose the other left. So anyway, so I'll sort of leave that aside. That's not something we need to worry about at this point. The basic concept that's behind was just saying and decided I better not go into, is that technically the definition of a strategy is that it's a complete contingent plan. It's got to tell us what a player is going to do at any point in the game whenever they're called upon to play. And so it turns out that in the game on the left, a simultaneous timed game, the column player has only 2 strategies, left and right. And the game I've drawn on the right, my sequential version of the game, we'd actually say column player's got 4 strategies, because we distinguish between choosing left after conditional on right or on down, and choosing left conditional on up. So that's something for another video. So anyhow, a strategy profile is a Nash equilibrium if no player has a profitable unilateral deviation. So if no player has a profitable unilateral deviation, then we have a Nash equilibrium. So in particular, the Nash equilibrium requires that nobody wants to switch their strategy. So we have a particular strategy profile, say upright, and to be able to ask ourselves, is upright a Nash equilibrium, it would have to be the case that neither player would rather use their other strategy. So let's go do this. Let's go find upright. In strategy profile, upright, column player gets a payoff of 10, row player gets a payoff of 0. Would either want to switch while the other continues doing what they're doing? Well, column player is pretty happy with that 10. If column player switches, column player would get 5. 10 is better than 5, so column player is not gonna change. So this looks pretty good at this point. What about row player? Well, if row player changes, row player would go from 0 to 1. That's better. Row player would actually want to change. Conditional on column player continuing to play right, row player would rather do down, right? And therefore, because row player actually does have a profitable unilateral deviation from the strategy profile upright, we know upright cannot be a Nash equilibrium. Okay, so Nash equilibrium requires no one wants to switch their strategy. Actually, turns out in this game there is a Nash equilibrium. It is actually downright. Okay, so how is downright the Nash equilibrium? Well, we can find Nash equilibrium by equilibria by searching for best responses. All right, so what's a best response? Best response is a strategy that yields the highest outcome for a player among their choices for a given strategy used by their rival. So best response is a really useful concept. It's the idea that among the things I could do, I've selected the strategy that gives me the highest payoff. If that's true, that particular strategy would be my best response. So for instance, think about the game where we play when we're walking down the hall, right? So you're walking down the hall, actually driving. Driving's a better one. So suppose we're driving, you can drive on the right side of the road or on the left side of the road, and the other person can drive on the right side or on the left side. If you're in the United States, our convention is drive on the right side of the road. So as you're choosing your strategy, do I drive on the right or do I drive on the left? And as your rival is choosing their strategy, drive on right or drive on left, turns out that your best response to them driving on the right is for you to drive on the right as well, because then you'll go by each other and you'll miss, right? Driving on the left, when the rival has chosen to drive on the right, is not a best response, right? Okay, so best response is a strategy that yields the highest outcome for a player among their choices for a given strategy used by their rival. So every strategy that my rival has, to that strategy, I have a response. And whichever is going to give me the best payoff is my best response to that rival strategy. So for instance, in this particular game, I've indicated row's best response to left is down. Okay, so if column player chooses left, row player can choose up and get 5, or row player can choose down and get 10. Well, 10's better than 5, so row player's best response to left is to choose down instead of up. Okay, and so I've underlined the payoff 10 to indicate that down is the best response for row player to left. It actually turns out row player has a best response to right as well. So let's go ahead and find that. So let's go ahead and have column player choose right instead. Suppose column player chooses right. What's row player's best response? Well, by choosing up, I get 0. By choosing down, I get 1. Actually, turns out row player's best response to right is down as well, right? Okay. So I've gone ahead and I've solved this game, actually. If we underline all best responses for each player's, following the method I've just described, then we arrive at the Nash equilibria, right? So it turns out 2 underlines in a cell indicate the presence of a Nash equilibrium, and that's this right here. The strategy profile down right, as I said before, is the Nash equilibria for this game. And so we found this by best response. It actually turns out that choosing down, when choosing down is row player's best response when column player chooses right, and choosing right is column player's best response when row player chooses down. And because these are best responses, nobody has a profitable unilateral deviation, right? By construction, because we have found that down right are mutually best responses, we know that no player can gain by deviating, which means indeed this has to be a Nash equilibrium. So 2 underlines in a cell in the matrix indicate a Nash equilibrium. The other way to say that, suppose we don't have a matrix, the other way to say that to indicate a Nash equilibrium is if both players are using their best response to the rival's strategy. Okay, so 2 underlines in a row indicate a dominant strategy. So notice down is underlined both against left and against right. That indicates that down is a dominant strategy for row player. So dominant strategy, what's a dominant strategy? A dominant strategy is strategy is dominant if it is the best response to the rivals, to all the rival strategies. A dominant strategy doesn't have anything to do with how I do in the game. What the dominant strategy means, for a strategy to be dominant, it means it is my best option, regardless of what my rival does, right? So the property of being a dominant strategy has only to do with the comparison between one player's own other strategies, right? And so the idea is that a dominant strategy is one that's always the best response. Now, not every game has a dominant strategy, or not every game has a dominant strategy for both players. However, if both players have a dominant strategy, the strategy profile picked out by mutual selection of dominant strategies will be a Nash equilibrium. Notice we have that in this game. I say down and right are dominant strategies. They're always the best response. So down is a dominant strategy for row player, and right is a dominant strategy for column player. And indeed, down right is a dominant strategy equilibrium. It's a Nash equilibrium. Okay. So now I'll show you a game that doesn't have a dominant strategy. So here, by this best response method, I've underlined each player's best response. So let me just do this in real time so you can see this. Suppose column player is choosing left. What should row player do? Well, if column player is choosing left, row player could choose up and get 3 or down and get 0. They'd rather go up and get 3. Suppose column player chooses right. What can row player do? Row player could choose up and get 0 or down and choose 1. Row player would rather would rather choose down and get 1 against right than choose up and get 0. Okay, so what about if we take column player's perspective? Suppose row player is hypothetically choosing up. Column player can either get 1 by choosing left or 0 by choosing right. Column player would rather choose left and get 1. 1 is bigger than 0. Suppose instead, hypothetically, row player is selecting down. What's column player's best response to down? Well, column player's best response is right. Column player would rather go right and get 3 rather than 0. So interestingly, here we have a game with no dominant strategies, because if I look, there's no row that has 2 underlines for row player's payoffs. Neither is there a column that has 2 underlines for column player's payoff. No row that has 2 underlines for row player's payoff. Oops, I didn't mean to do that. There's no column that has 2 underlines for column player's payoff. So that's important. So we don't have any dominant strategies. However, we definitely have 2 Nash equilibria, because the condition for Nash equilibria is that we have 2 underlines in a cell. And indeed, we have this up left and down right. So in this particular game, we have two Nash equilibria. So let me write this out. So the Nash equilibria are up left and down right. And notice, very important here, I have defined these Nash equilibria by strategies. A strategy profile is a Nash equilibria if no player has a profitable unilateral deviation. And to identify these Nash equilibria, I've used the strategies, up, left. It would be incorrect to say that the Nash equilibrium is 3-1 or that the Nash equilibria is 1-3. Why is it incorrect? Well, those are the Nash equilibrium payoffs, but the Nash equilibrium itself is defined over strategies. Okay, so every game has a Nash equilibrium. Many games have more than one Nash equilibrium, and not all games have dominant strategies. So every game has a Nash equilibrium. It may not be in pure strategies. It may require mixing. It might require a particular randomization between a player's strategies. However, every game has to have a Nash equilibrium. And then I can go ahead and show you an example of one where there is no Nash equilibrium in pure strategies. So this game is actually called Matching Pennies. And we can go ahead and test to see that there is no Nash equilibrium. Suppose column player chooses heads. Here's how the game works. We each have a penny, and we hide the penny from each other. And then at the appointed time, just like rock, paper, scissors, you show the penny to your rival. And if my penny is heads and your penny is heads, I take your penny. So I get one and you lose one. If my penny is heads and yours is tails, if they don't match, then you get my penny. That's how Matching Pennies is played. So, okay, so suppose I choose heads, or suppose you're column player, you choose heads. I'm row player, what do I want to do? Well, if I choose heads, I get one. If I choose tails, I get -1. And I'm doing this hypothetically as if I know what you're doing. Of course, when the game's played, it's played in real time, simultaneous. I have no idea what you've actually chosen. What I'm doing right now is sort of suspending disbelief. I'm saying hypothetically, if you did this, what would I do? This helps us identify best responses. Suppose you were choosing heads, or column players choosing heads. Shouldn't use you because this gets sort of ambiguous. So column players choosing tails. Row player, what does row player want to do? Well, if column player has selected tails, row player wins by selecting tails, right? Loses one by selecting heads. So column player, so row player's best response to heads is heads. Row player's best response to tails is tails. Suppose row player has chosen heads. What does column player want to do? Well, if row player has chosen heads, column player's best response is tails. And suppose row player chooses tails, what's column player's best response? It's tails. So now we have completely characterized this game. We have found all the best responses. We don't have any dominant strategy, and we don't have any Nash equilibrium in pure strategies. It actually turns out in this game, the Nash equilibrium, there's no cell with 2 underlines by this best response method. In this game, the Nash equilibrium does not involve a pure strategy. Instead, it involves the mixed strategy of playing each strategy half the time. Actually turns out you can show this. The Nash equilibrium for this game is if each player chooses heads and tails with probability 1/2. That would be a Nash equilibrium. So, okay. One last concept is something else we can do with sequential games. So this is called the Chainstore paradox. This is from Selten, Reinhard Selten, 1978 paper. Reinhard Selten was awarded the Nobel Prize along with John Nash and John Hersani, I believe in 1994, for their contributions to the development of game theory. So Reinhard Selten's, one of the major contributions was the concept of subgame perfect Nash equilibrium. I'm not going to introduce that concept here in this introductory video. However, I'll introduce the motivation for that concept. So suppose we have 2 firms. One is an incumbent in this market, and the other is a potential entrant. And our potential entrant has the choice between coming into the market to actually entering or staying out. And our incumbent has the opportunity to either accommodate the entry and split the market share, or to fight entry with a price war. So as this game is framed, suppose the potential entrant, or so what the incumbent wants to do, what the incumbent would like to do, is be able to threaten that it was going to engage in a price war. Like to threaten that there's going to be a price war. And actually, I could change these payoffs and make it a little bit more interesting. I don't know. It doesn't doesn't matter. I mean, the game is going to have the same properties, but I could make this a -1 here for the entrant. The top payoff is the payoff to the entrant, to the player, to the first player, and the bottom payoff is the one to the incumbent, to the second player. And what this incumbent would like to do is like to say, hey, if you come into the market, we're going to have a price war, and this is going to end up being super unprofitable for you. Therefore, you should stay out of the market, right? This threat of a price war should keep the entrant out of the market. However, that's not really what happens in this particular market for the following reason. The potential entrant's going to look forward in this game and say, hey, what happens if I actually enter? What's going to be the incumbent's actual best response to entry? But actually turns out, if the entrant comes in and the incumbent is called upon to play, turns out the incumbent's payoff to accommodate is higher, it's 2 versus 0, than the payoff to price war. So if it actually comes to pass that the entrant has come into the game, I'm going to highlight over accommodate, the incumbent's actually going to want to accommodate. So that's a problem, because now if we can figure this out, the entrant can figure this out. So the entrant realizes, hey, if I come into this game, I'm actually considering the payoff of 2 versus the payoff of 0, and I don't even have to worry about the payoff of -1 because it's not going to happen. So what's the entrant going to do? They're for sure going to come in. So it turns out the Nash Equilibrium, indeed for this game, the subgame perfect Nash Equilibrium for this game is actually in and then accommodate. And I spelled accommodate wrong. So anyway, what's the problem here? The problem for this game is that price war is not a credible threat for the incumbent to use. It's not sequentially rational. When it comes to pass that the entrant has actually come in, no longer is it in the incumbent firm's best interest. I said best entrance. If it comes to pass that the entrant has entered the market, no longer is it in the incumbent firm's best interest to fight entry. It's not a credible threat for the incumbent to use, because once entry occurs, its best response is actually accommodate. If we can figure this out, the rival can figure this out as well, and so we expect the entrant's actually going to come in. This is actually, apart from this sort of interesting realization about how we can get this insight about what could potentially happen in this entry situation, what I've modeled here for solving this game is actually the method for solving an extensive form game by backward induction. So backward induction is the process of using this sort of best response approach by going to the end of the game, looking at the last player, the end node player's best response, and then folding back, like I said, to the front of the game, where we then take on the perspective of the potential entrant, and we actually disregard the possibility of the subsequent player using a dominated strategy. And so that's what actually made this work, and that's how we were able to find our equilibrium. It actually turns out for a game of this form, backward induction will uniquely pick out, the backward induction solution will coincide with the subgame perfect Nash Equilibrium solution, though in more general games that result differs. So anyhow, so I'll go ahead and conclude here.